my lectures. It's my pleasure to introduce Matros, Yurii Matros, because I've had a long discussion with him about 20 years ago when I visited the Novosibirsk Center. He's now in US, so he's working in near St. Louis in Missouri, and he will talk this morning about forced and steady states, catalytic processes, positive and negative experiences.
First of all, I want to thank the organizing committee for the opportunity you gave me to have this presentation in centenarian birthday anniversary of my teacher and colleague Yurii Matros. I was very lucky to work with this very nice person and excellent scientist. He was a real catalyst for all of our research, for all of our work in the area of first unsteady state conditions in catalytic reactors. The main difference between reactors that are located in first unsteady state conditions and steady state conditions that we are trying to change some input parameters like temperature, concentration, the direction of the flow rate to initiate the conditions inside the reactor unacceptable for steady state conditions. We are trying to construct the field of the state of the catalyst temperature profiles, concentration profiles was more acceptable from the point of view of high selectivity, more productivity. This is the big difference between with processes realizing steady state conditions. Very shortly, I will try to share with you the information about the benefits of forced unsteady state operation for catalytic processes. Very shortly, I will show you the efficiency of changing the concentrations and temperature before the reactor. Benefits will be brought to from the point of view of increasing efficiency of the catalyst. But the main emphasis will be made on the real application. I will share with you with our experience and experience of another companies and our point of view about some positives and negatives what we have during the realization of first unsteady state processes in industry. As I told at the very beginning, in first unsteady state conditions I can create the more effective states of the catalyst, more acceptable from the optimal point of view, the concentration and temperature profiles inside the tank of the catalyst. It's a lot of possibilities to influence on the conditions inside the reactor. But unfortunately, through thousands of publications during the last maybe 20 years, it was a lot of success was shown in publications, but unfortunately only on the tip of the pen, unfortunately. few very simple examples. You can see the profiles of the temperature along the packed bed for reversible simple reaction, for cases when the inner temperature is very different. But in all cases, for exothermic reversible reaction, I need to have a profile when the temperature will decrease along the back bed. But in reality, taking into account that this is an exo reaction, the profile have the decline like it's shown in the picture. But I can tell you that in first unsteady state conditions, I can realize the process when the profile will be like a red line. We'll discuss a little bit later. Another example, very simple example. On the right side, you can see the profile of the dependence of outer temperature and the degree of conversion for simple case oxidized butene. Profiles or curves, dependence of concentration of or inlet outer temperature versus inner temperature. And you can see that I can achieve the level of destruction efficiency at temperatures like 240 to 150 degrees C. But if I will periodically change the inner temperature and organize the process when the same destruction efficiency can be achieved at temperature, average inner temperature like 160 is more than 100 degrees C less. For two advantages in this case can be used in reality. For reversible process, I can increase the degree of conversion because I will work at less temperature with the inlet of the back bed of the catalyst. And second, I can decrease the amount of the energy that I'm spending to reheat the gases before the back bed of the catalyst. Another example. In case if I will change periodically the ratio between hydrogen and nitrogen for the catalyst with catalyst or synthesis of ammonia, in this oscillating case, I can achieve the situation when the rate of creating ammonia is more than in comparison with the same conditions, but in steady state case. It's a lot of publications that are showing the efficiency of increasing the efficiency of the processes when the inlet concentration can be oscillating. Only Professor Sylvester with his team published, I think, near maybe 300 publications for different processes, and in every case he showed excellent results. Okay. This is, I will need a little bit later for good news that some, I think that 2 or 3 presentations have been discussed, in 2 or 3 presentations it was discussed the mechanism of Mars 1 travel. And I will not repeat, but I will need this diagram to discuss a little bit later one of the technology. Only a short remark that under this mechanism, the products of partial oxidation are primarily formed on pre-oxidized or lattice oxygen sites. Side products of complete oxidation are primarily formed on absorbed oxygen sites. And the contacting hydrocarbon only with pre-oxidized catalyst bring increase in selectivity. And the idea is, well-known idea, it was discussed, this idea also during this conference, the we're trying to separate oxidation stage and removal and reduction steps to increase selectivity and productivity. To divide stage of reduction and oxidation will bring the benefits. we'll discuss about the real application of this idea. Few words about the conservation process. We recognize that during the last maybe 15 years, it was maybe more, it was published maybe 500 papers, all 500 papers, what showed the efficiency to increase, to improve the process in first unsteady state conditions. But in all cases, in majority cases, I think in 99% cases, the experiments was made not with catalyst acceptable for industry. The process conditions are very different from what we need to have in real application. It's very low temperature, very small pressure, and unusually concentration. Small concentration, sometimes very high concentrations. But what I want to emphasize, and this is very, very important, please do by yourself sometime the very easy calculation. Try to simulate, try to estimate the transient period for the catalytic cycle when you will disturb one of the parameters like concentration or temperature. And you will see that the transient period is only few seconds in majority cases. Only few seconds. For the case when you will do the estimations more acceptable for practical application. Please remember these numbers and we will return to this a little bit later. Another method to realize the unsteady state processes is try to have the process in creeping heat waves inside the backbed of the catalyst. Even if preheat, suppose that we preheated the backbed of the catalyst, elevated backbed of the catalyst to the level where the reaction will take place. Let's introduce or let's give to the inlet of the reactor cold gases. Then after a very short time, you will see the formation and creeping heat wave along the backbed of the catalyst. It's good idea to try to realize this phenomenon that at cold inlet temperature you can see high temperature inside the backbed of the catalyst. And there is few methods to have this heat wave, to hold this heat wave inside the backbed of the catalyst. We will return to this idea when I will discuss about the real application. This is few methods of collecting, of having the hot place inside the backbed of the catalyst. It's well-known process, reverse process inside the backbed of the catalyst. 4 wells is changing, periodically changing direction of the flow rate inside the backbed of the catalyst. And this is the reason why at inlet cold temperature, outlet cold temperature, I have high temperature inside the backbed of the catalyst. During the last maybe 10 years published a lot of works where people propose different technological schemes that allow them to have this hot spot inside the backbed of the catalyst by different configuration of the technological scheme. But the idea is the same, to have this hot place inside the backbed of the catalyst with in conditions when the inlet temperature is relatively very small. And now about a few examples what will show you that we can have problems with the realization the ideas of first unsteady state conditions. This is all results what were shown by people from Institute of Katalysis like 20-25 years ago. two hot spots can be created. It was created exactly in the same place where we use the bucket to add the catalyst. And after, when we use more modern method of loading the catalyst on the right side, you can see that the hot spots disappear. And this is the reverse process for oxidation SO2 to SO3 in one packet of the catalyst with diameter 3 meters. Inlet and outlet is cold, but you can see that you have the cold temperature not only. No, I'm showing you this place. I need to show this place. Oh, I forgot. And you can see that the cold places was recognized near the wall, and this phenomenon created that maybe 20% of the gases are bypassed near the wall. And it was developed a few methods to homogenize, to equilibrate the profiles of the temperature inside. I will tell about this in a minute. Okay, and now about the main stages, what we have during the developing new technologies. First of all, we need to know, and we know a lot of details about the catalyst. Suppose that we know everything, including the kinetic data, catalyst is fine, good. And we began to think about possibility to increase the efficiency of this process in first unsteady state conditions. We made a simulation, discussed with our boss, with companies, and tried to receive the money because the results is excellent. Okay. And we have the money to do the lab unit, to do the tests in lab. After this, we have the possibility, to work, to design and work on pilot plant, and first commercial scale unit. This is the trivial stages for every process. But the problem is that with excellent results after simulating the process on the basis of the knowledge of the catalyst, good results in lab, but the first thing will appear when we will have the pilot unit. And the second, and a lot of seconds, will appear when we will build the industrial installations. And we know, because Fate decided that during the last 16 years we are working in industry. And before this 15 years we worked a lot of years in institute of catalysis in our alma mater. And we have rights, I think, to tell that yes, it's not so easy to go from piloting to the first commercial installation, and a lot of things will create a lot of problems. This is the slide where very shortly we try to summarize the name of these themes. The first, what is written in red, is genetic characteristics of the process. We cannot eliminate. They present in we have them. And first is short cycle. What I told at the beginning, short cycle because of very short transient period for the catalytic cycle. Second, that sometimes we cannot, it's hard to work in conditions when outlet compositions is fluctuating. In a lot of cases, industry cannot accept this one. Cannot accept the pressure jumps, what will take place in unsteady state conditions very often. concentration spikes. The reactor non-uniformities. This is for negatives for all cases, for steady state and unsteady states. But it's not the time to discuss why, but I think that you will understand immediately that for first unsteady state conditions, the unhomogeneous conditions inside, non-equal conditions inside, will be collected, and the influence will be more stronger in unsteady state conditions, because the negatives will be summarized, will be integrated during the first unsteady state conditions. And now, first example. This is DuPont process, very original process to oxidize normal butene to molecule in the system with with two separate fluidized beds. In one fluidized bed we have stage of oxidizing, catalyst after reaction, and second stage is riser system where the catalyst, where the normal butene will be oxidized to molecule. And very important to have a stage purge by inert material to dissolve the products of the partial oxidation, in this case molecule, right, from the surface. Okay. What they waited. This is well-known process. I think that maybe in the Institute of Catalysis also, I'm sure you discuss with people from DuPont about this process. There was a lot of publication, a lot of patents, and they waited for increasing the initial concentration from 2% in fixed bed or 4% in the fluidized bed to 20%. Why? Because they separated the flow rate with oxygen and with butene. And this is the reason why they had possibility to increase the initial concentration. They waited, and this is the main, to increase selectivity of the process. And everything was shown in lab. This is the results when they published. You can see that in comparison with conventional fluidized bed reactors, the selectivity increased significantly. And this is real data. It gave them high optimism about this process. But what we had in reality, this is the riser flow reactor on the right side, and you can see that the concentration of the particles below the bed is very different. It's very small in the center, very high in the beginning. Near the wall, a lot of particulates near the wall, the particulates are going down. The dispersion of residence time inside the riser is very high, and this means that we have a lot of catalysts, a lot of particulates are reduced, and a lot of particulates what didn't work because of high dispersion. Next, I'm returning to one of the main problems, short cycle, I told you. This means that for this case, I need a lot of catalysts to create a little bit material, a little bit product. Because concentration of the active sites on the surface where the process is taking place is very small. And this is the reason that to create 1 kilogram of the product, they need to have 1 ton of the catalyst for circulation. It's huge. And two main problems created the results. Is a lot of catalysts would need to be circulated, and problem with riser reactor, what I showed you, and the process died. I think that they spent maybe a lot of $100 million. Duration. It was very easy to estimate the duration of the transient period on the surface of the Earth. And I think that their answer, if they do this, their answer allowed them to cancel all of them. I will show you the name of the companies who tried to do the same. And it's not all companies. A lot of another companies tried to do this. Maybe they didn't publish, maybe they didn't write the strong patents. But this is examples, the name of some companies who tried to do the same. And I don't know the example when somebody has success in this area. Another application. It's, you know that a lot of years, maybe 20, 25 years, academia and industry try to develop new catalysts to reduce NOx, but not by ammonia, by hydrocarbons, in case when gas phase has a lot of oxygen. A lot of patents, a lot of publications, no results. We was involved in this business, and we waited and waited and waited for the catalyst. No. 15, 20 years ago, automakers developed new engines to work in lean burn conditions. This means that the ratio between air and fuel is much more than stoichiometric. It's allowed them to have very effective engine. But the problem of NOx, appeared. They needed to decrease what? Somebody help me? Please, I can hear it. Okay, finished? Thanks. But problem of NOx appeared because it's a lot of NOx appeared after engines. And I want to tell you that Toyota decided this problem. It's one of the excellent jobs that was made during the last years in the area of first unsteady state conditions. This is a typical unsteady state process. They developed a catalyst comprised noble metals and carbonates of alkali and alkaline earth metals. The source gas conditions alternates on oxidizing, it's lean burn stage, and reducing, this is rich burn stage. During the lean burn stage, NOx is stored as a nitrate. Hydrocarbons are oxidized over noble metal catalyst, and the last stage is rich period when NOx is reduced into nitrogen by hydrocarbons, or it can be reduced by syngas. The first method was developed by Toyota, and today we